In exercise 17, we were given the state space representation of a Dublin scar, written in terms of the Cartesian coordinates. In part 1, we were asked, does the system have a point of equilibrium? The answer is, it all depends on u. If u is different than 0, then we know already that the function f equal to x dot has its third row different than 0. So there won't be an equilibrium state. But if u is exactly equal to 0, this ensures that the third row of the function f is set to 0. While x dot and y dot can't vanish simultaneously, we know that the velocity is equal to radical x dot squared plus y dot squared, which is equal to radical cosine squared theta plus sine squared theta, which is equal to 1. So in the case where u is equal to 0, we know that the heading would be constant and the velocity would be constant, and this is considered to be equilibrium. Now in the second part, we were asked to transform this state space representation into a polar representation using alpha, d, and phi. This was solved on a piece of paper, and I would provide the handwritten solution. For part 3, we were asked, why did we do this transformation? And the answer is because if the state space representation is represented using the polar coordinates, the robot would be easier to imagine and visualize because of its rotational symmetry. So in other words, it would be more intuitive for us to imagine the state of the robot. As for part 4, we were provided with a certain control load. So what this control load does is that it is continuously checking on the angle phi, which would reveal the direction of the motion of the robot relative to the origin. So if phi was to be 0, the robot would be heading to the origin, which is here, origin of the neighborhood, and if it was 360 degrees, it would be also doing so we won't talk about it. But if it was pi or minus pi, it would be heading away from the origin. So in the first case, we check if cosine phi is less than 1 over radical 2, which means we check if phi is in between 45 degrees and 315 degrees. If that was true, this means that the robot is currently heading away from the origin. So what the controller does is that it sets the input u to 1, meaning that the robot would turn robot turns to the left. This prevents the robot from continuously moving away from the origin. And for the other case, it's considered to be proportional control. Obviously, in this other case, phi would be in between minus 45 degrees and 45 degrees. The control would be minus sine phi, and it is in fact proportional, because as the absolute value of phi increases, the absolute value of minus sine phi increases. Which means that the correction would be more aggressive, because the robot is heading with a bigger troubleshoot towards the origin. But as the absolute value of phi gets closer to 0, this would get closer to 0 in absolute value, which means that the correction of the heading of the robot would get smoother. And as for the simulation of the control law, we were given this code. What it has over here, it has first of all the function f of x, which is this one, but with the first two rows multiplied by 5, as you can see over here. And then we have the control law. First of all, for the control law, we attain the function alpha, the value alpha, using the function arc tangent 2 of y over x, and we know that we know that phi minus theta plus alpha is equal to pi, and that's why over here we calculate phi by setting it to pi minus alpha plus theta. So we do those two checks to specify in which of the two states the robot currently is, and we could run the code to see the simulation starting off with any of those three initial states of the robot.